I'm staying here because I'm going to do demos again, so it's a little more, it's a little easier for me. So we saw before the geometry, and a few things have been added in the mesh at this point. You've all seen already the aided mesh generation, which come with the software, but at this point we've improved it a little. So again, the mesh generators that we have here is a mesh generator that doesn't need any specific information from the user. Now, of course, you can always overwrite any of the information, but it doesn't really need anything from the user. It's going to try to respect, of course, all of the geometric features, and it also uses the geometric features to find the proper mesh. It will by the way, if you bring a file from a previous version and you are trying to use this new mesh generation, it will automatically overwrite all the information that it had from before. You can do global settings, and as I say, you can control locally, and you can also, and this is be done by macros, you're going to be able to make a mesh which is specifically associated to such things as skin depth. So that's just the way it looks, and I'm going to show it to you, so I won't go too far at this point. Just know that to be able to use it, it's activated here. So if you bring an old file, you may have to set the activated field. How everything works, well, it's actually trying to define a distribution. So if I have, it's going to take the geometric features of the device, and it's going to try to find the initial mesh density, and it will try to spread it. But as it's spreading it, it will also try to increase the mesh. So what the goal is always to have the best mesh possible with the less element possible. So I'm going to demonstrate this in a minute. Just some example of the mesh. Those are mesh where the user didn't do anything, but the program actually was able to create all those weights and everything there. So let's go back to our little image from before, and we're going to clean all the mesh. And the first thing I do is say edit mesh. And I'm going to make sure that it's activated here. And so the different, I could actually set a value of point everywhere and set it, force it, but I'm just going to do it dynamic so that the program is allowed to do whatever he wants. Then this is actually going to define how many, it looks at the dimension of the device. And it's going to try to define how many nodes it needs looking at the full dimension of the device. And then this one is going to see how from a little mesh it's going to grow and try to limit the number of mesh. So let's put it as it is by default inside the software. So I'm not doing anything. I have not assigned anything, and just for you to understand that yes, indeed, I have not done anything. I think I have a way to reset the mesh. No, it's not here. I can, yes, somewhere here. If I go inside there, I can clean all the mesh information, and that is done by this one. So it says clean all mesh information. I say yes. So definitely there is nothing that is done, and I'm using exactly the problem as it comes out from the geometry. And I'm going to do just the mesh. So here I did mesh along the line, and in fact it didn't do very much. Let's just ask for the full mesh. And here is what I get. So now I'm going to go back to the edit mesh, make sure this is activated. I'm going to actually change some of the distribution. And let's redo the mesh. And here, no, let's remove the stuff. So the only thing I did here, you can see what I did is actually came up with a very, very small information here. it tried to control how the mesh goes along the line. So the only thing I did here, mesh edit, is I actually control how fast the mesh can grow. So I put 25 here, and now that's what I have here. So I can change those values, and we can see how it would affect the mesh. Let's put, for example, 0.1. This is 0 is the smallest one you can have. You cannot have 0 actually. And if I do this, I say OK, and let's redo the mesh. And you can see now that I have a density a little bigger. So, and I can do the same with the faces, and I can do the same, of course, with the volume. Now let's see, make sure that I have a name for this region. I do not have a name, so we'll create a new name and call it coil. And what I want to show you is that there is a special features now, which is the mesh skin depth. So let's assume that this was a solid piece of copper, and the solid piece of copper. So I would have eddy current right on the surface, and actually to do the mesh properly, I would have to make sure that I am indeed making 2 elements within the skin depth. So let's see, I don't remember the dimension, that goes from -6 to +6, it's 12. Okay, say for example I was somewhere around 100 hertz, so probably the skin depth would be around maybe 3 millimeters. So let's see, we have the macro, which is right here, that was loaded before. So I'm going to call it macro coil. You can say it says mesh skin effect face regions. It's going to ask me how many layers I want within the skin depth. I'm going to put 3. It's going to ask me for the size of the skin depth, so I'm going to put 003. So that's actually let me put 2 just to make sure we see something. What's this? I said from here to here it's 6 millimeters. I'll put it even smaller. Sorry, 1. And then I said to which region it's going to be affected. And then eventually I could exclude some line. I'm not going to exclude any lines. I'm going to say OK. And it's creating all the information. I don't have to worry about anything. And here is the skin depth. And you can see I only have the layers on the surface of the mesh, and I have nothing in the middle. So doing this, I was able to concentrate my mesh and make sure that my mesh was correct for the physics problem I'm trying to do. So let me not, let's go a little further. So that was the information I was just giving you on the skin depth. And just to go look at it, that's exactly the same example I showed you, and the way it's actually working. Now remember, the skin depth is in meters, so you should make sure that you put the right information right there. So we just did this. Let's talk a little more of the new version. So we have the solving process has been a little changed. The integration and the assembly were already parameterized, parallelized in version 10.4. In version 11, we've added 2 new solvers in version 11.1. And those are a MUMP and Paradiso solver. The Paradiso solver is very good on Intel, actually one type of Intel processors. It's really is amazing what it does. Sadly, it's actually a solver which is distributed by Intel, so that's probably one of the reasons. It's not as interesting on the other. I just missed the name of the other processors, but anyway, it's not as good. AMD, yeah, thank you. It's not as good on AMD processors and some of the older Intel solver either. However, I mean, we can see an improvement in certain cases. It is not really where we would like it to be. You It is not really where we would like it to be. We're still working on it. And let me tell you that in fact we're working on a multi-node version, so that you are going to be able to delocalize computation on different nodes. Something we brought back in the solving that we had a long time ago and had lost, it's the adaptive time step. So that's very interesting when you solve transient problem. And those transient problems have very nonlinear function happening. So you can actually set an initial value of the time step, a minimum and a maximum. And then the program will be able to adjust the time step within those parameters to match the signal. So how do we define this? Well, it's important to define a maximum time step so that the program doesn't get crazy and misses some of the nonlinear changes in the signal. And then the minimum is because in some cases the program would not be able to, it would try to reduce and reduce. So this is, by the way, a prediction correction algorithm, so it's going to try to solve something. If it finds that it changed too much, it will come back and redo it with a small time step. Post-processing, this is all inside a single environment, and I'm going to actually show you some of this just in a minute. Important part, we can do composite curves, so the curves can actually go all over the space. It can be closed on itself or not closed on itself. Let's see, now you can get directly normal and tangential component. For a while we couldn't, so this is back on. And this is trying to look a little more like the old legacy tool. There is a new box for the computation of quantities, and what we have added is we have added the possibility to copy directly the result, to move them somewhere else. We can do computation on faces, volumes, physics items such as point region, line region, phase region, volume region, and circuit components. You'll see them, they're already brought here directly. I'll show this in a minute. In fact, right now. So what I did is that my plan was actually to take you through the whole design of this, but just to make sure we have enough time to do everything we have to do, I'm going to show you the result directly. So this problem was actually solved for a varying current, and in fact we can look at it, not varying, but the magnitude of the current that was varying. I used a scenario. Here is the scenario. So that's how I define, by the way, for people who don't know, that's how we can define a scenario. So we would have any parameters that are here, and then I can define any interval. So this one I'm going from 0.01 to 20, and I ask for a 100 value, and here are the different values that it's computing. I can always add to a scenario. So I'd be able to add more solution behind. And when I control a scenario, it can be by step value, step number, or list of steps. In this case, I cannot do adaptive because it's a variation of a parameter. It's not a time variation or anything like this. So this is solved. Here is the result. Flux lines. Okay. Same as before. So again, the environment has changed. If you remember before, we had a very big post-processing window here. We split it up, and now we have only the solving that appears and everything associated to the post-processor. So here we have the data exchange, something I would use to do frozen new or send information to a third-party product or do permeability, flux, Riemann flux density freezing. Support, I can define the different type of support. So that spatial support may be a group of faces, of regions and things like this. Electric groups, paths and stuff like this. The graphic, the curves, computation, and then the advanced are things that were actually available from the geometry before. So I can actually check the mesh, I can look at parameters and stuff like this. So let's talk about this case here, and the first thing I can do here, not this one, so let's take this one. In fact, let me just do it live. So I'm interested in knowing the inductance of this coil. And let's just quickly look at something I have here. Here we go. There are many ways to actually compute the inductance, but just for reference, some of the common ways that people use, and in fact there are other ways where you can do a step function. I haven't actually added it, and where you can also do a transient. This is not in your slide. It's just a little stuff I had on the side. So sometimes we refer to linear inductance as L, which is the flux divided by I. It's a funny way. I'm not really sure that any electronic circuit can see it, but some people refer to it as this. So in this case, phi is the flux linkage, I is the line current, and L is the inductance. There is another thing that people refer to as local inductance, and this is just an L equal d phi di. So it is how much flux can I add with adding more current, basically. Okay? This one is probably a little more the one that magnetic, the one that electronic circuit drives and stuff like this. C, not this one, but this one. This is another one for the mu, and this is because whenever I have a magnet in it, so if I were doing the magnetic, linkage flux integration with the magnet being on, I would also get the flux of the magnet. If I don't put it on, then I would not have the proper pictures of saturation. So I have a possibility to basically solve a first time, remove the magnet, and now solve and compute the linkage flux. This is what we call the frozen permeability. And then another one here is by energy. So you probably know the energy is actually, I think there is a problem here. It's actually 1/2 of Li squared, I'm really sorry. And so you can get the inductance out of there. So I want to show you that you can do all of those inside flux. So right here, I've computed this versus current. And the first thing I can do is get the flux. So the flux linkage, I've created the sensor, which is called flux. I will show you what's inside the sensor, but basically this is the flux for the current increasing. The sensor is, where do I get the sensor? Right there, sensor. And if I look at the flux, you can see it's just a normal flux. It's called predefined quantity, and it's a magnetic flux, and it's on the coil region. So this curve that I have here is flux this way, current this way. So the first one I can do is flux divided by I. So very easy to do. I have this curve here. I'm going to do here the flux divided by the current, and the current is an input right here. And here is my curve of flux divided by the current. So that would be the linear inductance for different value of the current. It has to change because the saturation changed. So you cannot have the same one, of course. Now, most of the time when you do a measurement on a rotating machine, you have permanent magnet in it, and this actually creates a saturation. So the saturation, or the picture of the saturation of the machine, may not change very much after with the current. You have some field weakening or stuff like this, but maybe not as much as just a magnet would be. So you would not probably see as much of change as I can show you here. But anyway, so that's the first one. I did say that the derivative was another way. So if I look, I did my curve, I think it's not this one, sorry. Here, this was my flux curve from before. Well, this curve, actually I can do a right mouse click, and by the way, look what I can do. I can edit, by the way, I can export it, in fact, in an Excel, but I have other things like integral and derivative. So if I derivate this, I have I in X, and I have phi in Y. So I'm going to get d phi di. And let's try to do this right here. So I'm deriving this one, the flux curve, and it's the one in yellow, and I don't really like the yellow, and I don't know why it comes in yellow by default. I don't really like it. Here we go. And here is my curve. So that's the flux. The L computed, it's what's called sometimes the local inductance. And I can actually put them on top of each other. So I have the one, let's see, this one, where is my others here? This is the flux divided by the current, and this is a d phi di. So let's superimpose two of them. If I go into the curve here, 2D curves versus IO parameters, and I can superimpose two curves. So one is going to be evolutive 2, and the other one is going to be evolutive 3. Let's just say OK. And they're all here. Let's just put them on top of each other's absolute. And I'm going to remove the flux because I don't really need it. So let's go see here. I'm removing the flux. Here it is. So now I put on the screen here the two different inductance. This is a linear inductance, and this is a local inductance. You can see there is quite a difference here. And this is what can make a success or a failure when you try to drive the machine. Because if you send this to the guy who does the drives, he's not going to be able to do a drive for you. Okay? Now let's look at the other one. There is another one, and I'm actually, just to go a little faster, here it is. I have put it somewhere else. I have the energy. I think it was this one. No. I need to find them back here. Ah, that's the one which is divided already. Okay, never mind. I have the energy, so I'm going to look at the energy versus position, so versus current. Here is the curve of the energy. And again, so we don't see as much effect of the saturation because it's in I current squared and stuff like this. But I can do the division, energy divided by 2 times the current to the square, and that is going to give me the L. And this is the L computed from the energy. Now again, this curve works only if I don't have a magnet in it. If I have a permanent magnet in it, this is not going to be good because I will have an offset of the permanent magnet. And it's not going to give me how much energy the program is capable, the device is capable of storing. And so let's see, I think I have all of those curves superimposed somewhere. Maybe not here. Let's see, superimposed one. Maybe this one. Yeah. Here we go. I'm going to put all of them on top of each other. And I'm going to remove the flux one. So flux, where is the flux? Right there. Flux, I remove the flux, and here I go. Now, what do I have here? The yellow one is phi divided by I. This one is d phi di, and this one is energy. And by the way, you can see that the computation from the energy is very close to what we really want to have, right there. Okay? So just to show you the type of computation you can do in Flux in the new post-processor. And let me just finish my presentation here. Another thing that we have done here, we can create a file, a startup file from a transient startup. So which means you can go up to a certain position, and then you can use, for example, you do a steady state, and you're going to try to do a failure, you can restart from the last step of the steady state. And this cube, so that's actually a question that I had all before, so now we can rebuild the image of a skewed problem. Now, keep in mind that this is an approximation, because in this case, when I do the skew, I'm actually solving in the middle of the slices and I look like if they're straight. So I can bring back some stuff, but there is definitely a little thing that are added there. So I told you there were quite a few macro in Flux at the end. So we have this, in fact, they're all available on the support site now. But some very good macro, total harmonic distortion. What do I have here? Extraction from a 3D curves, format flux result and stuff like this. Current regulators, for example, there is a macro to define the current regulators directly. And sorry, I went one too many. Then we have analysis of two curves. We have min max of a value on the region, min max of a value on the global quantities and stuff like this. And then finally, today we have actually 57 macros, but I think we have more than this. And those macros come from the application team. They come from some people from the development team and some users who do this. So I would encourage you, if you have any macros that are very cool, to share them with us. We love to share them with a lot of people. So as I say, macro your flux. Just to close here, elegant system design solution. That's the last ad we did. And I just want to make you aware of the fact that we are also on virtual media. So you're going to find us on YouTube. And in fact, you can go see some cool animations on YouTube. There is Magsoft Corporation and Cedrat Simulation Software. And you can also find us on Facebook and on Twitters. And I think on this, I'm going to, I guess it was anyway a scheduled break, but